To ensure predictable behavior, all transactions have to possess the basic ACID properties. They have to be atomic, consistent, isolated, and durable. So atomic means that a transaction must work as a unit, which is either fully committed or fully abandoned when complete. A single transaction can consist of any number of operations. And so that means that they must all succeed or they have to all fail. A transaction also needs to be consistent. This means that all data has to be in a consistent state when the transaction is complete. All data integrity rules have to be enforced, and all internal storage mechanisms must be correct when the transaction is complete. You can think of a transaction as a transition from one consistent state to another. Transaction also must be isolated. This means that they have to be independent of the data operations of other concurrent transactions. Concurrent transactions can see data changes only before other operations are complete or after other operations are complete. And then it needs to be durable, which means that after the transaction is complete, the effects are permanent even if system failure occurs. And there's various features built into SQL Server that help enforce these conditions. Now, the ACID test is part of the ANSI SQL 92 standard, a fairly old standard at this point. And so SQL Server fully supports the ACID test by supplying several features. One is locking. Locking facilities preserve transaction isolation by making sure that multiple transactions can't make conflicting changes to the same resource at the same time. So locking is a very important feature of using a relational database engine such as SQL Server. Another feature is logging. Logging ensures transaction durability. Even if the server hardware, operating system, or SQL Server itself fails, SQL Server uses the transaction logs when it restarts to automatically roll back any uncompleted transactions to the point of system failure. And then there are also transaction management features that enforce transaction atomicity and consistency. After a transaction starts, it has to complete successfully, or SQL Server undoes all the data modifications that occurred since the transaction started. These ACID-related features of SQL Server, and in fact any modern relational database system, are the major benefit of storing data in a database as opposed to text files or other basic storage types. SQL Server manages these features for you so that your data is always protected and its integrity kept intact. And transactions are the primary vehicle for hooking into the benefits of these features. Now, SQL Server supports three types of transactions. One is explicit transactions. These you have to explicitly start by issuing a begin transaction statement within your code. Then the commit statement commits an explicit transaction and saves the changes to the data. This is what makes it permanent. And then there's a rollback statement that rolls back the transaction, that undoes all changes within that transaction at that point. The @@TranCount system function tracks the number of open transactions so that you can keep track and perform different actions based on the level or the number of nested transactions that you're currently involved in. This explicit transaction gives you complete control over an operation's transactions, and you can include as many or as few operations and statements within the transaction as you want. You have complete control over it. Then the next kind of transaction is an auto-commit transaction. This is the default mode for SQL Server. In this case, all individual statements submitted to SQL Server are automatically committed when they're complete or automatically rolled back if a problem occurs. The database engine is in this mode outside any explicit transactions or until you turn on implicit transactions, which is the next transaction type. In the implicit transaction mode, SQL Server automatically starts a new transaction after you commit or roll back the current transaction. You don't have to do anything to start a transaction. You can control this mode using the T-SQL set implicit transactions statement. The on setting causes each statement to start a new transaction automatically after completion of a transaction. And the off setting returns SQL Server to auto commit mode. And by default, transactions are managed at the connection level. When you start a transaction on a connection, all transact SQL statements that execute on that connection are part of the transaction until the transaction ends. Each transaction has to end with either a commit or a rollback statement. A commit statement guarantees that all modifications are permanent. The rollback statement backs out all modifications that the transaction made by returning the data to the state it was in at the start of the transaction. And both commit and rollback statements free the locks and resources that the transaction used. Another important concept with transactions is isolation levels. An isolation level defines how much a transaction is isolated from changes made by other concurrent transactions. The current isolation level setting determines the side effects that can occur due to uncommitted changes that other transactions make. SQL Server supports all 4 of the isolation levels defined in the SQL ISO standard. That's the standard that defines the structured query language specification. And then there's a couple others that are related and supported in SQL Server related to row versioning. The first one supported in SQL Server is read committed. This isolation level is in effect with auto-commit transactions. It ensures that every transaction meets the requirements of the acid test without requiring extra code. So you don't have to write any additional code in order to get the benefits here, as long as the isolation level is set to read committed. So this level prevents concurrent transactions from reading uncommitted data or interfering with the transaction until it's complete. This level results in locks on resources that could affect concurrency and the volume of transactions that a server can handle. And I'll be talking more about that. The next level is read uncommitted. This isolation level lets other transactions read changed data that's not yet been committed by other concurrent transactions. And these are sometimes called dirty reads. This isolation level doesn't issue as many locks as read committed, so has a lighter touch on resources and allows higher transaction rates because more transactions can be doing more things because not as many resources are blocked from being changed. Then there's the repeatable read isolation level. This is similar to read committed in that the transaction can't read changed data not yet committed from other transactions. But it goes a step further. This level prevents other transactions from modifying data read by the current transaction until it completes. The benefit is that a transaction at this isolation level can repeatedly read the data and get the same results, even if there are other transactions pending. Then, the serializable level, which is the last of the levels specified in the SQL standard. This is similar to repeatable read, but it takes it up a notch. Serializable prevents both updates and inserts. It ensures that if a query is reissued inside the same transaction, existing rows won't change and new rows won't suddenly appear. To do this, it employs a whole bunch of locks that prevent edits, deletions, or insertions until the transaction is complete. The snapshot isolation level essentially saves a snapshot of data at the start of the transaction to ensure that any data read during the life of the transaction is going to be the same as at the start of the transaction, no matter what changes have been made to the data in the meantime by other transactions, although the current transaction will see its own data changes. This isolation level generally doesn't require locks on data until the current transaction attempts to update the data. And then there's the read committed snapshot. This is similar to snapshot, except that instead of providing a snapshot of the data when the transaction started, read committed snapshot provides one when the statement started. The behavior of this level is similar to read committed, except that it doesn't acquire shared locks and the changes aren't blocked when resources are exclusively locked. Okay, so these are some pretty subtle differences. I wouldn't worry for now about a lot of the details, particularly with some of the more esoteric versions of these. Take away from this that there are a number of different isolation levels that affect the data that a transaction is able to read and its current state. So that's the biggest thing. And then as you start developing more Transact SQL applications and you start having problems with concurrency or seeing data, or you want to see data that's not quite committed and so forth, then you can start to explore some of the other options. Now, in order to set the transaction isolation level, you do that using the set transaction level statement. And then there's also a table hint that you can use for a specific query using a with clause. The important thing about isolation levels is that they can affect what data your code reads when there are other concurrent transactions executing. The choice you make of the isolation level can significantly impact the amount of activity an instance of SQL Server can support. So, if you have performance issues on a heavily used database, you might want to tweak the isolation levels used by your code. But for the most part, the defaults are going to be fine. So that's the nice thing about the isolation levels. One of the ways the relational database protects data from corruption is by locking data and other resources during the course of a transaction. A lock prevents certain operations on the locked resource. And then locks remain in effect as long as the transaction is active. For explicit transactions, that means until you issue a commit or rollback statement. When data is used in read-only operations, such as a select statement, SQL Server places shared locks on the data. Once the data is read, the lock is quickly released. Row-level locking was introduced way back in SQL Server 7.0, and each subsequent version of SQL Server has improved locking strategies in order to reduce their impact on a server. Now, SQL Server uses a dynamic locking strategy in order to determine the most cost-effective locks for an operation by performing calculations that correct the granularity of locking for your specific operations. For instance, a select statement that reads all the rows in a table would expend more resources if it were to use shared row locking rather than page-level locking or table-level locking. So rather than locking a whole bunch of individual items, it can use less granular locking mechanism at a page level or a table level that are going to include multiple rows. Now, SQL Server performs the calculation behind the scenes and determines the most efficient lock mode for any given operation. In other words, the lock that is going to perform or provide the protection that it needs, but have the lightest impact on the server. You can override this mechanism with lock hints, but for the most part, you should avoid doing so unless you have a very good reason. And usually there's some sort of a performance problem or a problem where SQL Server is not coming up with an optimal execution plan. The nice thing is that for the most part, SQL Server does a great job of selecting appropriate locks. Now, one thing about this, for query execution plans, SQL Server calculates what's called the cost of an operation. This isn't the cost of the work and money. Fortunately, Microsoft doesn't, well, at least doesn't yet, charge you for every operation in SQL Server. The query execution cost is a performance measure that SQL Server uses to determine which of several possible execution plans is most efficient. And it provides a basis for comparing different queries and plans. And when you get into studying execution plans, you can look at the details within Management Studio. Then you'll see the relative costs of different kinds of operations. Now, if you need to get information about locks that are on the system, there's several different mechanisms that are available. So some of them include the locks event category in a SQL Server profiler trace. There's also a dynamic management view that returns information about currently active lock manager resources. You can also use the SP lock procedure and sys lock info, the compatibility view, which are included for backward compatibility. You can also use the locks object in System Monitor, which is called Performance Monitor in earlier versions of Windows. And then you can use enum locks in SQL Server Management Application, or an SMO application. And for more information about getting information about locks, you can check out the Locking in the Database Engine topic in SQL Server Books Online. It has a lot of detail about locking and monitoring locks. One of the issues that you're going to have to deal with at some point is block transactions. The idea here is that although locks are a major way that SQL Server protects the integrity of your data, you have to manage and program them carefully to avoid problems. The biggest problem is that blocking happens when transactions are blocked by other transactions. In that case, the blocked transactions just sit and wait. On a network, blocked transactions will either hang or eventually time out with an error message. In general, not a good thing. I want to show you an example now of how the read committed isolation level affects concurrency. And in this, I'm going to use an explicit transaction. All right, so I have an instance of Management Studio. So I'm going to begin a transaction. I'm going to execute just this code right here. And what this is going to do is it's going to update categories to change the category name from seafood to ocean fruits. So I'll go ahead and execute that code. All right, so that query executed successfully and all is good. Now I'm using the default isolation level here of read committed. Now I'm going to go to a second instance of Management Studio. I have that same file open. I haven't executed the rollback transaction yet. But now what I want to do is I want to use Northwind and select category name from categories. And I'll execute that. Very simple query, should execute very quickly. But it doesn't. So as you can see, it's executing the query, and we can sit here twiddling our thumbs, waiting and waiting and waiting, but it's not going to go anywhere. The reason is that this new query in the second instance of Management Studio is being blocked by this currently executing transaction in the other instance of Management Studio. And by the way, you can't do this in a single instance of Management Studio, because if you try to open this transactions.sql file in the same instance, it'll just keep coming back to the single version. So you have to use two instances of Management Studio. Okay, so we're sitting here, executing the query. Even though the query has completed in this first window, I haven't committed or rolled back the transaction, and so SQL Server is still holding the locks for this update statement. So in essence, this transaction is blocking this transaction here, because there's an implicit transaction going on behind the scenes. Okay, so I'm going to go back over to my first window and now roll back the transaction. And now when I come back over to the second window, you can see that the query executed successfully, and I got the list of categories. Because as soon as I rolled back the transaction in the first window, it no longer blocked the query in this window, and it was able to finally proceed and return the results that I wanted. So that's the basic idea of blocking. Now I'm going to go back over to my first instance again. And I'm going to do basically the same operation, but I'm going to start out by setting the transaction isolation level read committed. Now, this is actually redundant code because that's the default, but I just wanted to make it very clear that that's what's going on here. All right, so I'm going to execute this code here. And once again, it executes successfully, but I still have a pending transaction that I've not rolled back. I'll go back over to my second instance here and scroll down. And now what I'm going to do is I'm going to select from categories, but before that, I'm going to set the isolation level to read uncommitted. Remember that read uncommitted is going to let me read dirty data. performing what's called a dirty read. All right, so I'll execute this code, and notice that the code now executes immediately. But what's really interesting here is that the value that I get for this category is ocean fruits. So I'm seeing the change from the first transaction. Remember, that's what this first transaction is doing. It's changing it from seafood to ocean fruits. So even though this transaction is pending, it's been neither rolled back nor committed, because I set the isolation level to read uncommitted, I can read dirty data. The data has, in effect, already been updated in the table, but it's just not been made permanent yet. And so this select statement is no longer blocked because it doesn't need to be, because it can read dirty data. Okay, so if I go back over into my first instance here and I roll back the transaction, I can come back over to my second instance, re-execute that same query, and you can see that it's been rolled back to actually seafood. Results are in a slightly different order. So this shows the effects of different transaction isolation levels on concurrent transactions. Now imagine that you have thousands of concurrent transactions, and you can begin to see the importance of properly designing the transactions you use in your databases and applications. One very serious situation that you might encounter is something called deadlocks. Deadlocks are possible when too many locks are held for too long. And specifically, a deadlock occurs when two separate processes each hold a resource that the other process needs. Each process waits to free the resource that it's holding until the other resource becomes available. Okay, so the way this works is that we have a couple of resources. Maybe these are a couple tables, some other resource that I want to access through my transact SQL code. And I have two transactions. Transaction 1 is accessing resource 1, and so it has some sort of a lock on resource 1. Transaction 2 is accessing resource 2, and so has a lock on resource 2. Then, as transaction 1 continues, it attempts to get a lock on resource 2 because it needs to use that data, maybe to join the data together, to updates, whatever kind of process it needs. But it needs some sort of a lock on that resource. But it can't get it because transaction 2 is holding a lock, some sort of exclusive lock on resource 2. So that doesn't happen. And then transaction 2 attempts to get a lock on resource 1, but it can't because transaction 1 has a lock on it. So that doesn't happen either. So at this point, both transactions are blocked. They each need a lock on the other's resource, but can't get it because the other transaction is holding that exclusive lock. So this is what's called a deadlock. And at this point, absent any intervention by either you or SQL Server, things are just going to sit there being blocked forever. Okay, if SQL Server or you do something to get rid of a transaction, it goes away, then transaction 2 is finally able to get the lock on resource 1. It can continue to execute because it has access to the resources that it needs. Okay, so that's basically how a deadlock works. Now, SQL Server uses a set interval to determine which processes are running and which are blocked. If that interval passes twice and a process is still blocked, then SQL Server will choose a deadlocked victim. And in general, this is going to be the transaction that is least expensive to roll back. And when it rolls it back, it generates an error code 1205, and you can capture that error within your code, the code that caused the transaction to execute. And then, when you catch it, you can either resubmit or cancel the query. And then you have a little bit more control because you can also specify the priority of a session by using the Set Deadlock Priority setting and choose either low, normal, or high, or by setting the priority to an integer value in the range of -10 to 10. A deadlock priority of low maps to -5, normal to 0, and high to 5. So using the words versus the numbers is just a different way of getting to the same place. But the numeric values provide a wider range of options. Most of the time, though, the 3 named levels are quite adequate for handling the situations. And the deadlock priority defaults to normal. And then SQL Server chooses a random victim when 2 sessions have the same deadlock priority and the same cost in rolling back the transaction. Deadlocks are very difficult to simulate in a development environment. The problem is they seem to appear only when your database is running and when a whole lot of users are attempting to complete the same operation at the same time. But there are some practices that you can use in order to prevent blocking and deadlocks. Essentially what you're doing is you're avoiding creating situations that can cause severe blocking. So I have several suggestions for you. One of the biggest one is to always access objects in the same order. Back in that previous slide where I had T1 and T2 and resource 1 and resource 2, if both T1, transaction 1 and transaction 2 access the resources in the same order, one process would get a wait queue while the other transaction is able to complete successfully. And then once the one transaction completes successfully, the other transaction is able to continue on. So always access resources in the same order. But that can be kind of difficult to do in multiple stored procedures. You also want to avoid user interaction in transactions. The way you want to do things is to collect all necessary input from the user before initiating transactions. If you start a transaction, then ask for user input, you set yourself up for blocking issues because inevitably that's when the user is going to decide to go to lunch, leave the transaction open and pending, decides to take the rest of the afternoon off and don't come in until the next morning, and in the meantime all of these other transactions are trying to get access to the resources. And so the moral is avoid user interactions within transactions. Keep transactions short and in one batch. The longer a transaction holds resources, the more contention will occur for those resources. Use as low an isolation level as you possibly can, because a lower level translates into greater efficiency, because SQL Server uses fewer locking resources to ensure data integrity. It's a lighter touch on the resources within the database. Avoid recursive and nested triggers. Triggers that fire other triggers can cause a cascading transaction tree that lengthens the duration of a transaction and then blocks other processes. And then probably my best recommendation is to avoid coding errors. So a little bit tongue-in-cheek, but a begin tran in an explicit transaction without a commit or rollback will lock resources indefinitely.